Hi everyone, welcome to the first video I'm going to make in this series of analytical technique tutorials. This one is going to focus on k-means clustering. I'll first hopefully look to discuss the theory of this analytical technique with you, and also discuss the reasons for this method and the way in which it's theoretically applied. Alongside this video, I'm going to provide you with a second video which is going to look at the application of this in our studio, and this will be a step-by-step guide of how we can use this analytical technique in a practical setting. Within this video we're going to discuss clustering and k-means clustering. So unsupervised data is data which doesn't have a label, and therefore we look to create clusters of instead. We can use k-means clustering on labelled data, however this is done later on and we use it to compare the data against rather than use it within our method. We're going to look at clustering, so the way you group things. We're going to look at k-means clustering, and we're going to use this structure which we'll use throughout the different videos that we do. We're going to have a look at use cases, so it's where it's used, the actual algorithm itself and the theoretical application of it, and then the practical application of it. We're going to, in this case, determine the optimal value for k. So k-means is a k in k-means clustering, and this is a value that we set. And we're also going to look at the diagnostics, or if you've done k-means clustering well. And also we're going to have a look at the reasons to choose and the cautions of this method, which we'll get into a little later on. So clustering in general is how we group things together. That's what we're trying to find out. We're trying to find out similarities and relationships. It's not a predictive method. We're not trying to predict anything for the future. We're looking at data that's already there, and we're trying to work out patterns within that data. So how do I group these documents by topic? How do I group my customers by purchase pattern? We need to sort the items into groups by similarity. We need to look at how similar they are to each other element within that set of groups. We need to look at details of the properties and the characteristics of these similarities, or detail the properties of distance and the inverse of that similarity. So if we think about an example, if we think about when you get on a plane, some people get a plane sickness. It used to be, when you used to go to the doctors and you used to say, I've got a phobia of planes, I've got plane sickness, they used to give you one of a set of drugs. Each one of them drugs could have worked or they couldn't work. So they did this test, or did a clustering test on this scenario, and they worked out, they had a look at the patients, they had a look at different symptoms, and they had a look at the outcome of the drug that was provided to them. What they found out was there wasn't one type of plane sickness, there was two. So there's two different types. Because of that, when they found out, they worked out they could give this one set of drugs to these people and they could give this set of drugs to this people. One of the good things within this, when it comes to clustering, they managed to work out that the symptoms, they clustered the symptoms together within this method, and they worked out with giving drug 1, it looked at like head, and it was a mental capacity. And if they give drug 2, it fixed like a stomach and a physical aspect. So there was two distinct different ways of dealing with this, and clustering allowed them to look at this data, bring the data together, and then give the business problem some information in order to solve it. So overall, clustering is looking at bringing data together and similarities and relationships. It's not predictive, but it's looking at how we can look at data and look at trends, and then we can take it forward. We're going to focus, however, on k-means clustering. So k-means clustering is a type of unsupervised learning used when we're using unlabeled data. Okay, so the aim is to partition observation into k clusters, in which each observation belongs to a cluster within its nearest mean. So what that means is, in essence, is we're going to look at the average, so that's what means is, a mean element, but we're going to give it a k value first. So we're going to, for instance, as a data scientist, say, I want my data to be within 5 different clusters, so k was equal to 5, so 5 means clustering, and then we're going to look at the average of them 5 clusters, and then we're going to try and find out how similar different elements within them stages are, and then we're going to bring it together, and we're going to try and find patterns. So in order for us to do this, we need to have an input, and this has to be numeric. It has to be numeric because we need to be able to work with the data. There must be a distinct metric defined over the variable space, or as they call it, a Euclidean distance, and all that means is a point from 1 to 2. So if we're playing golf, for instance, you tee off from this 1 point, and then the ball lands at a certain point. That distance between them 2 points is the Euclidean distance, and for our scenario that we're going to use, it's just going to be the difference between two numeric values. And then from that, we're going to produce an output, the centres of each discovery cluster and the assignment of each input datum to a cluster. So basically, again, it's a lot of complicated terms that they use, but it just means the centroid or the mean. So we're going to input some values into our k-means cluster. We're gonna give it a value, k-means cluster, and that's dependent on how many clusters we want as a data scientist. But there's also like a clever way, which we'll cover later, of how you can kind of work out how many you want to use. We're going to look at the number of k-means clusters that we want, and then we're going to look at the similarities within that based upon the Euclidean distance or the distance between them. And then we're going to look at the centroid, and the centroid is just the mean. So it's the average of everything together, okay? So what we're actually looking at is we're looking at the mean of data, but it's a way of doing it in order to allow us to put into a set of clusters. So looking at k-means clustering and the use cases or the examples of how this can be used, it's often used as an exploratory technique, and it's generally looking at the structure of data. So we're trying to find out trends within data or within the clusters that we're going to create in order to see if symptoms and properties and attributes within them are similar to other elements. And then from that, we should be able to find out trends. Sometimes it's a prelude to classifications. So if you're trying to classify something, so it could be, for instance, like a health risk. If you're trying to classify it between red, amber and green, within them 3 stages, we might set k-means clustering to be in 3 stages. We might run this on a set of data, and then we might find different symptoms and then work out different elements within the process, which will then allow us to classify the attributes and symptoms within a set of clusters. And then it's just a way of separating data and looking for similarities. Some examples that we could look at, for instance, we could look at the height, weight and average lifespan of animals, and we could do clusters based upon each one of them. We could look at household income, yearly purchase in dollars or pounds, number of household members of customer households. So with that example, we could be looking at different parts of data, and then we could be looking at how a trend of pattern within someone purchasing something could be done, and then how we could look at say I buy something on Amazon and you buy something on Amazon. I will look at some different trends and different characteristics that we've got similar, and then see if we can blend trends and look at that sort of elements. We could look at patients' records within measurements of stuff like BMI or cholesterol levels. We could look at cluster regions across the country based on sales, sensitivity risks. So these are all, there's millions of different examples that you can use for use cases, but the main thing to get across is k-means clustering is an exploratory technique, and it's looking at structure and trends within the method in order to find similarities between attributes and data. So we've got an example here to have a quick look at. The background of this example is it's looking at a retailer who have offered returns on any products that's got purchased with an unlimited lifespan. So I can buy something and then I can send it back in 6 months' time or 2 years' time, it doesn't matter. So if you have a look at the 3 graphs, you'll see that we've got little tiny dots and we've got big dots, and we've got a set of 4 keys or 4 clusters. It doesn't matter what these are yet, so we'll just call them 1, 2, 3, 4. Within the cluster itself, we've got all these little observations, the little tiny ones, and then we've got the mean or the centroid of that cluster as a bigger dot. Okay, so all that bigger one is, it's the mean of all the clusters together. And then we've got the return rate and the purchase frequency at the top, and then we've got the lifetime customer value, which is just like a term which means the importance of that customer to the business. And then this is split up in between the return rate of the customers here, and then also the purchase frequency of them customers based on the ones that return stuff. So we've got like an overall, we've got a return rate section, and then we've got the purchase frequency based upon that. Okay. You can see from these graphs that the purple, for instance, the purple don't purchase as much here as the other groups probably do, but they also don't return as much as the other groups would really do. So within the data itself, that group of people, a high lifetime customer value customers, because they're purchasing stuff and then they're not returning it, even though the other groups, if you look here, generally are doing. If you look at the red one, for instance, they're generally purchasing infrequently, and their return rate is again less than what the purple is. So them set of characteristics and symptoms kind of similar. With the blue or the teal colour, they're generally the normal customer, if you can say normal. So the return rate, they are returning some items, but their purchase frequency again is quite high, which is good. So if you look at the purchase across here, the life cycle, they're still based upon the purchase frequency and the return rate, they've got quite a similar line. Then we look at green, the final one. These have got loads of activity within the characteristic group, so they're probably buying lots and lots of different things. They might be buying stuff in like different sizes and that sort of element, but then they're also sending a lot of stuff back. So even though they're buying loads and they're sending loads back, their lifetime customer value is less than the other three groups putting together. So it might be good looking at clustering to work out something such as this, then have a look at the characteristics within these sets of groups afterwards, and then we can work out if there's a way of getting more money or more customer experience out of the first set to make them come back continuously. So this is just a quick way of looking at over this data and trying to find trends and patterns within it. So this is the algorithm then. Okay, so first, step one, you need to choose K. So you need to choose the random centroids in this example. So we've chosen 3 different points. So we picked the blue point here, the red point here, and the green point here. There is an equation to work out the distance that you put between these, but generally you can put them where you like as long as there's a good enough distance. You won't want them too close together because you won't be able to find different trends and patterns. So you generally spread them out as much as you can. So step one, we've decided that K equals 3, so we're going to pick 3 cluster points. If we decided that K equals 5, we could pick 5 cluster points. The way we pick how many clusters is generally a subjective thing based upon the size of data and the different variants that you think as a data scientist you're interpreting this, what it could be. However, there is other ways later on where we can change the value of K, and we can do methods within RStudio and programming to allow us to do this more efficiently. So after we've done step 1 and we've picked our centroids or our mean averages, we then look at step 2. And step 2 is looking at assigning each of the observations, so each of these little tiny dots, to our main dot. And the way we do that is through the Euclidean distance, or the range, or the closest point to our mean. So if we've chosen these 3 points here, so we've got 1, 2 and 3, if we're using this observation, we find the closest one of these points to that based upon distance, or the Euclidean distance. I keep saying that just to make sure you remember it. And then we colour code it based upon that one. So we've got all the blue ones around here, and then we've got all the red ones around here, and we've got the green ones around here. At the end of it, each of these observations should be assigned to one of these cluster points that we've chosen, or the centroids. So after we've assigned observations to each of the centroids, we then need to recalculate the centroid. So we need to look at all the observations that are there, and we need to recalculate based on an algorithm which I'll show you in a minute. We need to recalculate it. These centroids will move into the right position based upon what we're looking at. So we'll look it from there, and it moves across. So at this point here, it's moved from here, which is the first one, based on the average. So we've done all the observations and it's here, and now it's moved up because out of the observations that are around it, the central point or Euclidean value of that is now moved up to that point. So you'll see like the little colours, they slightly move. And then step 4 is to repeat step 2 and 3. So in essence what we're going to do is we're going to pick 3 different points, the k values. We're going to assign all the observations to one of them k values, or to a centroid. We're then going to recalculate the position of that centroid after we've assigned the observations to it based upon an algorithm, and then we're going to repeat this step over and over again. So we're going to look at the centroid's position, we're going to assign observations to it, and then we're going to move the centroid based upon our observations, and then we're going to then recalculate the observations and assign them to it again, and then so on and so on. And then we'll continue doing this until the centroid doesn't move anymore. Eventually it's going to work out the average for you based upon the algorithm, which is kind of where we're going with it. And then we can work out the mean or the similarities of them different data points based upon that centroid itself. So this is the way we will pick k when we look at program, we look at RStudio. So it's to find the elbow of within sum of squares, or the WSS plot, as a function of k. So this is the algorithm. It means WSS is equal to the sum, which is what that symbol is, the number of clusters k, times by the sum of n, which is the points of I within that cluster. So the number of clusters and the number of observations which are connected to that cluster. Don't worry, you don't need to remember this. And then from that you'll get a graph that looks something similar to this. So you'll have, if you separate your data in between one cluster, so it's one big set of data, generally the value of a total within sum of squares is over 1600, so it's super high. If we then start to break it down into different clusters, so 2 all the way to 15, you'll see the elbow, which is at number 4, which works out the elbow is the plot within k. So you've got 1600 here, and it goes all the way down to 2, 3, 4, and then you'll see it slowly here starts to straighten out again. The number of clusters or number of iterations that we then test this upon needs to be like a subjective view of the number of difference it's going to make. So it's good doing it like it is here 4, 5, 6 times to work out the number of clusters that you can separate your data within, but there's no point doing it after we get to like 9, 10, 11 based upon this, because the centroid position isn't moving enough. So we need to work out, because obviously if you're using massive sets of data, if we're running one test on 2 clusters of data, so we're just separating it between 2 sets, so we're taking loads of data and separating them into 2 pieces, that's going to take a lot of resources to do. If we're separating it then in between 3 and 4 and 5, it starts to get higher and higher and higher. If the centroid or the average of that section isn't moving very much at all, at that point it's not going to make a massive difference into your observations and your findings afterwards. So it's a bit of a common sense element you have to put into this. But this is the actual equation you use to pick the k. But we're going to do it via programming anyway, so you don't need to know this. You just need to have a quick look over it and make sure you get the gist of what it's doing. What we're trying to find out really is we're trying to find out where the elbow is. So you've got cluster number 1 is dropping all the way to cluster number 2 here. So there's a massive difference in that, which we could do an evaluation just on 2 clusters and we could compare them 2 together. And then we've got 3, 4, we've got separation bits which are quite massive within that optimal number of clusters here. And then after number 4 it starts to bed down, it starts to lower. Obviously the number of clusters could go up to the number of observations you've done. So if you had 6 pieces of data which you were clustering, it could only ever go up to 6 because each individual piece of data would then be in its own cluster. So obviously you're generally going to work with much bigger data than that, but that's something to consider. So you just need to work out the elbow or the point at contact where you can then do justifications based upon all of these. If we did an analysis on 1, 2, 3, 4, 5, 6, these ones here might skew the data slightly, because you can see like in 4, 5 and 6 this happens, in 1, 2 and 3 this happens. So it's a bit of subjective common sense. So looking at diagnostics and the evaluation model, These are just a few questions you could consider. So do clusters look separated in at least some of the plots when the pairwise plots of this cluster? So pairwise is a method you can use instead of using variables when there's not much difference, and it's just a way of looking at a range of different scatter graphs next to each other. So you could make a scatter graph based on k-means 1, k-means 2, k-means 3, and you can do a comparison across that. That's one way of getting around a lower variable data set. Do you have any clusters with few data points? So if we've separated our data into 6 different clusters, and one of the clusters only has one data point within it, then it might be a case of decreasing the value of k in order to absorb that smaller cluster within our bigger clusters, and then we can look at different trends. Are there splits on variables that you would expect to see but do not? So are some of the data, are they combined within the clusters when they really probably shouldn't be? That's generally a case of if you've done like k-means clustering 3 and there's a massive range of data, you probably need to increase the value of k so you can get different pockets of clusters. So for instance, if we're doing a traffic light and we only did k-means testing 2 and there was only red and yellow, sorry, there was only red and green, and then we were doing it based upon cars going through the traffic light at a certain point, it might be a case of that defined state between red and green isn't enough, so we need to have the orange state in there so we can work out different elements within that. So a way of getting around that again is to look at increasing the value of k. So do any of the centroids seem too close to each other? So have we got a centroid average there, and what if we've got another one right next to it? If we try and decrease the value of k again, that generally that's similar to having clusters with few data points. That will absorb it, and then it should make the trends and the patterns within looking at it much easier to look at. And then finally, do the means of variables used for clustering vary across the clusters? So do the means of these variables used do the means of variables used for clustering vary across the clusters? So are two sets of them variables very similar? And the way we get around that again is by absorbing it, so we decrease the value of k. So you can see like the main diagnostics to look at are the data themselves and work out whether we need to add more k or reduce the k value depending on the cluster with few points. Is there anything you think should be split up? Are the centroids too close to each other? And do the variables vary across the clusters? And then also, if the variables themselves can't be looked at the same, then we can use something like a scatter graph or a pairwise. So that just means putting two scatter graphs next to each other, and then we can look at the variables compared to each of the scatter graphs. And you'll generally find that if you do it that way, you'll see, for instance, that on k-means 1, they might be scattered everywhere, but in k-means 2, they might be a lot more tightly connected in certain places. So you'll be able to decide based upon that whether you think you should increase the k or decrease the k. And then finally, k-means cluster and the reasons to choose to do this method, or the cautions against cations. I'll change that. The cautions as to why you probably shouldn't use this method. So the reasons to choose it are: it's easy to implement, so there's an algorithm set up ready, so we can use it straight away. It's easy to assign new data to existing clusters, and which is the nearest cluster center. So if we've got new sets of data that we're adding to existing sets of data, it's easy to understand because of that. It's got a concise output, so the coordinates of k cluster centers are going to give us a value or give us a trend to look at. Some of the cautions to consider: it doesn't handle categorical variables, so if you're putting data in between different categories, it struggles to handle that. Some of the it's sensitive to the initial value you give it. So if you give k-means testing the second value to start off with, it's sensitive to that, and you have to consider different variables and different outcomes because of that, because it's subjective. You need to look at variables should be all measured on similar or compatible scales. So some of the data you might be looking at might be on different scales, so it might be on like inches to centimeters or height to different elements. One thing you have to do when you're using this method, you need to put all the data you've got into the same scale to start off with. One of the cautions to consider is the number of clusters. It must be known or decided in a way that's based on theoretical deduction. So you can, if you were guessing, if you were looking at a data set that had 30,000 different pieces of data, and then you chose to do k-means clustering 2, and it turned out that was nowhere near enough, that could look at, it could hinder resources that you've got available, and it could hinder different elements like that. So you need to consider, you need to plan what sort of k-means testing you're going to do before you actually do it. And it tends to produce round or equal sized clusters, and this sometimes isn't desirable. So if you were doing a measurement on say the symptoms of the example we used before, so if we're looking at getting in an aeroplane and whether you're afraid of that situation, if you were looking at different sets of drugs to then look at the symptoms you've got and compare it against, if we separated the data based upon the cluster into 2 different sections, you might have 4 different sets of drugs that you need to then work out which ones would work with different symptoms. So sometimes having like a finite set of clusters isn't the right sort of thing, and each one of them sets of clusters will generally finish with the same amount of observations in, and it could mean that, say you've got 100 different observations, really 70 of them might be symptoms to drug 1 and 30 might be symptoms to drug 2. However, this method will generally pull out 50-50, so some of the data in the middle might be pulled into the wrong category. So that's one thing you need to consider. So hopefully this has gone over what k-means clustering is, and hopefully it's give you some of the theoretical content. So if you want to go to the second video, and then that'll look at the applied elements, and then it'll look at how we're then going to use that within RStudio. Thanks.